This is lecture 4 of the game theory and vaccination. One of the main objectives, one of the main things that we do in this lecture is the derivation of an expression for Nash equilibria. So we have to remember we're working with mixed strategies as the theoretical game is formulated in the context of epidemics with vaccination policies. So there are mixed strategies, and in that context, we are going to derive expressions for equilibrium points called Nash equilibrium points. So we've seen this definition. We're just revisiting, right? Two players play a strategy is called Nash equilibrium, then neither of them can deviate from this strategy and at the same time increase their payoff. We could rephrase this with the following wording. If most of the population adopts a strategy P and individuals that adopt any other strategy Q always obtain a lower payoff than those adopting P, then we say this strategy P is Nash, a Nash equilibrium point. Okay, we have seen this concept of equilibrium basically relying on that there is no force pushing towards a different outcome. So we had seen before how there was a relation between Nash equilibrium and another definition that we call evolutionary stability. Um, you will start seeing some things that are similar or parallel. Okay, so now we want to enhance the notion of convergent stability. And this is phrased with the following wording. If most individuals adopt strategy Q, but individuals adopting a strategy that is closer than Q to P obtain higher payoff than those adopting Q, then P is said to be convergently stable. So immediately, perhaps if I can convince you or persuade you, this idea of convergent stability, you should start um, drawing analogies, parallels with the notion of dominance. Okay, let me see if I can persuade you even farther about what is this idea of dominance. So if P is a Nash equilibrium and everyone is currently playing P, then no one should change strategy. Furthermore, if P is convergently stable, this idea of convergent stability has to do with somehow with dominance, okay? And this, when I say dominance, um, I am specifically referring to dominance over the quantification of payoff, okay? Higher payoff drives which strategy is dominating over other strategies. So if P is convergently stable, then regardless of what strategy is most common in the population, individuals should start to play strategies closer than P and ultimately adopt P. Okay. So you will see the initials C, S, and E, initials that stand for convergently stable Nash equilibrium. Now, let's bring some of the expressions that we had previously worked with, bring them here to the front line. So we had previously derived an expression for the expected payoff. And let's now suppose that the proportion epsilon of the population vaccinates with probability P, and that the remainder 1 minus epsilon vaccinates with probability Q. So right away you may think that this epsilon 1 minus epsilon and the probabilities may be factored into some kind of weighted sum or weighted average. Okay, so we define the payoff function relative to strategy P as E sub P, and we write the function we had previously defined, evaluated at capital P. And okay, so one thing to note here is that the previous expression that we defined for the expected payoff can be written, can be thought of as a function of two variables, q, as what we have written here, right? Two variables. The second variable, okay, the second variable in this expression only plays a role on this probability of infection. Basically, that is telling us what is the level of vaccination uptake. So, in defining this expected payoff relative to P, we observe here that the second argument is given by this sum. This is the sum that incorporates the proportion vaccinating with one probability versus the proportion vaccinating with the other probability. So that's sum, the sum that has the epsilon 1 minus epsilon as the weights, okay? And that is a P is a probability, Q is a probability, epsilon and 1 minus epsilon are weights that are in the scale 0 to 1. So this sum is still a probability, and that it will be the level at which the infection, the probability of infection will be considered. It will be considered probability of getting infected exactly when these many individuals are receiving immunization in the population. So let's see what goes next. This is part of what we were pointing out. This expression involves thinking on the index here in pi sub p as that index being evaluated, being equal to that expression. In other words, we would say that vaccine coverage matches vaccine uptake. Okay, this is now putting mathematical expressions in something that we had mentioned in words before, right? Uptake and coverage are one and the same. Now, the expected payoff for individuals playing the strategy Q is this function evaluated at Q and also evaluated at that weighted sum that we had just discussed. So let's now do an evaluation, do some derivation. So let's see. We have maybe if I can, I'm gonna write something here. I'm gonna say P. I'm gonna call this P tilde. Okay. I'm gonna call P tilde that weighted sum, the sum of epsilon capital P plus 1 minus epsilon times Q. Okay, I'm going to call that P tilde. So the first expected payoff is something that looks like minus R times P minus 1 minus P times pi evaluated at P tilde. Okay, that would be E minus P. And then we have to subtract, and this is where things are going to get interested. We have, you're subtracting here, so that is going to make everything in that expected payoff is going to switch signs, right? So this is going to become R Q minus 1 minus Q times pi sub P tilde. Okay, So we're adding up these quantities, and so that means that this um, is something where we have common factors. So I'm going to write R here multiplying minus P plus Q. And let's see, we have also a common factor pi sub P tilde. We have that common factor, let's see, and this easily before I proceed, I want to point something out here, and that is the following. You have to look at something that's in here, okay? That negative, this negative sign has to affect this, in fact. So that is supposed to be a plus sign. So this should be plus, right? Therefore, when we factor pi sub p tilde, okay, as a common factor, we have so when we factor pi sub p tilde, we end up with this expression. So now this is going to this negative one cancels with that one, and we can make this look like this. We have minus r times p minus q plus pi sub p tilde times p minus q. Okay, and so we can write here one more line in which we write p minus q as a common factor, and this multiplies minus r plus pi evaluated at p sub tilde, which is that expression we have over there. Now let's remember the dimensionless SIR model. Okay, it has this form, and this model has this probability of infection at a level lowercase p. Remember that p is the vaccine coverage, right? It's a parameter that appears here in the model for the compartment of susceptible individuals that are not protected against, that they are not immunized, they're not protected against infection. Okay, so you would like to really think of this probability as an expression that is evaluated a specific value of coverage, of vaccine coverage. So we're now, and remember this R was the new parameter that we defined, that is the relative risk, right? It's defined in terms of both the morbidity risk from infection and from vaccination. Okay, so if a vaccine is perceived to be sufficiently risky, then think of pi sub 0 as a situation in which the vaccination coverage, okay, the vaccination coverage is 0. So it's basically what's happening to think of this expression when you evaluate that little p equal to 0. Okay, so this is so exciting, right? There is still more calculations and more derivations that we have to complete. And what we're going to do is that we're going to continue this conversation into another lecture. So do not go anywhere, stay tuned, and we will resume exactly at this part of the lecture.